So, good morning my dear students. We have started from the last class eigenvalue problems. Eigenvalue problems. I had given the definition this x is equal to lambda x. This type of equation is called an eigenvalue problem, where this lambda is a scalar, A is n by n matrix, x is a vector. Okay. So, we need to find the value of lambda, the scalar and x, for x not equal to 0, that we had discussed in the last class. Okay. We had also discussed that we had already studied about these eigenvalue problems, and earlier you were finding as determinant of A minus lambda I is equal to 0. From there you are getting characteristic equation corresponding to this lambda depending upon the order of the system or order of the matrix. If I have n by n order of this matrix, I will get a characteristic equation of degree n when I have n by n matrix. Then to find, so this characteristic equation of degree n is in lambda. Okay. So, to find this lambda I need to solve this nth degree polynomial. Okay. And then if I get that those will be the lambda values, and then again I substitute here lambda values, and I will find corresponding to each lambda the x. That means, for lambda 1 I have the corresponding eigenvector x 1, lambda 2 x 2, each of them have n components. If you have the A matrix as n by n, if you have 3 by 3, then it will be this will be 3 component vector, like that. Now, I was discussing why we need to again study this eigenvalue problem. I told that if it is nth degree polynomial, I need to solve that nth degree polynomial, but it is not easy to solve always to find all the eigenvalues. Now, first of all, see that where from this type of eigenvalue problem we get from an application problem that we had last class we had started that. So, if I have this spring mass system having m1 m2 two masses, k1 k2 are the stiffness of the spring. Okay, fine. And if I take the displacement of mass 1 as x1 and mass 2 as x2, then I can write the differential equation of this system. Moreover, I also showed you that if I have two masses like this and having k1 and k2, m1 and m2, so this system is nothing but this. Fine. Now, this system, physical system, I can have the differential equation as mx double dot plus kx is equal to 0. Mx double dot plus kx is equal to 0. This is a second order ordinary differential equation, where this x double dot is d2x by dt square. Fine. So, this capital X will have how many components with respect to this problem? 2 components, because I have x 1 and x 2. Remember, this x is your x 1 and x 2. Fine. So, this I get by using the Newton's laws of motion. From there I can derive this, where these matrices for this problem may be given as m1 0 0 m2. You see, this matrix is a diagonal matrix, where the diagonal elements are m1 and m2 the masses. K is your k1 plus k2 minus k2 minus k2 k2. Fine. Here the K matrix is having all these stiffnesses of this springs. So, this is your mass matrix, this is your stiffness matrix. Now, I told that this can be transformed to an eigenvalue problem, fine. So, to do that, how I can solve this differential equation mx double dot plus kx equal to 0 for this system? We will assume that this is a simple harmonic motion. So, if it is SHM simple harmonic motion, so then I will assume this x, and remember till now this x is a function of what? Displacement x and time t. So, this I can write, if it is an SHM, I can write as phi x for x displacement e to the power I omega t. This you know from your previous classes, that if it is simple harmonic motion, I can write this capital X as these two functions, where phi is a function of only x and this is the function of t. Now, let us substitute this in the given differential equation. So, what we will get? What we will get for x double dot? For x double dot, that means I have to differentiate 2 times. So, if I differentiate 2 times, I will get minus omega square, I square will be there. So, I will get minus omega square phi e to the power I omega t, okay, that is fine, plus k, then x is phi e to the power I omega t is equal to 0, fine. So, if I substitute this x, which is a function of small x and t, that is displacement and time, like this phi x e to the power I omega t, I will substitute this here, I will get this equation. Now, you see here e to the power I omega t is not 0, is not 0, otherwise our assumption that this is simple harmonic motion will not be valid, okay. So, this is not 0, so whatever remaining, that will be 0, fine. So, what I am getting from here, minus m omega square phi plus k phi is equal to 0, fine. This I can write as k phi minus m lambda phi is equal to 0, where lambda I have taken as omega square, fine. We assume that m can be inverse, means we can take the inverse of m. So, what I will get? M inverse k phi, I am multiplying from the left the m inverse. So, this will be what? Lambda I phi or lambda phi is equal to 0. Now, m inverse k, if I assume a sum matrix A, so what I will get? A phi is equal to lambda phi. What is this? So, what we are getting? A phi is lambda phi, that means A x is equal to lambda x form, understood. So, this problem whatever you are doing, now convert it to eigenvalue problems, understood. So, this lambda I need, why this lambda I need? Because lambda is omega square, that means frequency. For the design purpose, I need to have this omega. So, if I get lambda from there, so I can find the omega. Similarly, if I find lambda 1, because if depend upon how many lambda depends upon the matrix order, whether it is repeated or not depending upon the matrix type. Okay. So, if I have lambda 1, I can find phi 1. So, phi 1 is what? If it is a 2 by 2, for this it is a 2 by 2 I have taken. So, this will be a 2 by 2, phi will be also 2 by what? 2 by 1, okay? 2 elements will be there. So, that means that lambda 1 you can find there, and phi 1, after substituting lambda 1 you can solve for phi 1, then for lambda 2 again phi 2. So, what are those physically? Phi 1 is actually this is the deflected position of this, how it deflects in the first mode, that is lambda 1. For lambda 2 I have phi 2, that means see for phi 1 these two masses are going in the same direction. If you solve that, you can see if I give some m values and k values. Okay. Now, the phi 2 will be maybe one mass will be going this side, other mass will be going this side. So, this will be maybe like this. Okay. So, this is with respect to the second mode. Okay. So, now you have understood the application, why we need to solve like this eigenvalue problems. So, this is only one example, one application problem where I have shown that this differential equation can be transformed to eigenvalue problem and eigenvalue problem then I need to solve. So, for 2 by 2 matrix I have 2 by 2 system. If I want to have 50 story or 50 masses, 50 springs, so you have 50 by 50 matrix. So, I need to find then the eigenvalues, fine. So, this is the cause that we need to study the eigenvalue problems with respect to different applications. Okay. So, now you have understood that how we get an eigenvalue problem corresponding to different application problems. Now, I will have one theorem, by that you can actually, by seeing the matrix, you can have the interval or the include, actually this is called inclusion of eigenvalues, where you can find, you can have the idea of having the eigenvalues in which area or in which intervals. So, this theorem actually is Gerschgorin theorem. This theorem tells you to find the eigenvalue bounds very easily. Okay. So, now this theorem states that if lambda is an eigenvalue of an arbitrary matrix, then for some integer j matrix you can take as A, that is maybe A j k. Elements are given by A j k, j is 1 to n, k is 1 to n. Okay. So, now integer j, where this j is lying between 1 to n. So, if lambda is an eigenvalue of an arbitrary matrix A, then for some integer j we have absolute value of A j j minus lambda less than equal to absolute value of A j 1 plus A j 2 plus up to A j n, but you will not have A j j here, means the previous will be A j j minus 1 and A j j plus 1. Okay. So, this gives the actually this will give a disk depending upon this lambda. Okay. I will show you by an example, means first symbolically, if you have a 3 by 3 matrix, suppose A 1 1, A 1 2, A 1 3, A 2 1, A 2 2, A 2 3, A 3 1, A 3 2, A 3 3. So, this theorem gives an idea about different disks corresponding to the eigenvalues. As you know, if I have 3 by 3 matrix, at the most how many eigenvalues I can have? 3 at the most, because those 3 may be repeated, may be different, maybe 2 different or 2 repeated, 1 different. Okay. So, at the most 3 eigenvalues are possible, maybe those are lambda 1, lambda 2, lambda 3. Now, the procedure is this for this theorem. So, I will have different disks depending upon these lambda 1, lambda 2 and lambda 3. Disk, I have the center, I have the radius. So, this d1 on the plane, okay, xy plane or lambda plane. Center I will take the first element, that means a11 with sign. If it is minus, it will have minus, and the radius I will take the summation of the absolute values of other elements in that row. Understood? This is with sign, first diagonal element, then radius will be other elements in that row with absolute values. This will give the radius. Next, this 2, a22, this one, and the other elements absolute value as the radius. So, it will be a21 plus a23. Third is d3, and this is your a33, and I will have a31 plus a32. So, now I know the center and radius, I can plot those. Okay? I can plot those. Suppose I want to plot this, and depending upon the numbers, suppose this a11 is somewhere here, it is positive suppose. So, I have this a22, a12 plus a13. Suppose I have the distance like this, radius. So, I can draw a disk using this radius. This is your d1. Suppose this a22 is this side, and I have the radius like this. So, I have a disk like this, and this is your d2. Suppose this a33 is here, and the radius is like this. So, d3 is here. So, this theorem tells that you have 3 eigenvalues, where the 2 eigenvalues will be in this d1 union d2, d1 union d2. If those are real, so it is from here to here. This is the bound of the eigenvalue. It cannot go less than that or cannot be higher than this. d3 for the third eigenvalue will be from here to here. So, you are getting a bound depending upon these elements whatever you are given. So, this gives an idea that your eigenvalues will lie where, means if you are doing some mistake, you can say those are not in that bound or in that disk. So, the whatever solution may be wrong. Okay? So, this gives an idea. So, let us take one example with respect to this and see how you are getting the idea of those eigenvalues in with respect to the disk. So, locate, question is locate the region of eigenvalues. Given the A matrix as 0, half, 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 5, 1, half, 1, 1. So, this is the given matrix A. I need to find the region. So, I will make that disk and center, radius, so d1 center is 0, radius will be half plus half, that means 1. Here by chance no negative is there. Okay? So, here if it is minus half, it will be half plus half, absolute value I told. Okay? So, it is 1. d2 5, half plus 1, 1.5, fine, 1.5. d3 1 again, and this is your 1.5. Understood? So, you got the center and radius. Remember, here all are positive. Suppose this is minus 5. So, you will have here minus 5. Okay? And accordingly other elements absolute value addition. Minus 5 means this will be in the this side. Okay? So, let me draw now. So, if I have 0, 1, 2, 3, 4, 5, 6, 7, 8, this side -1, -2, -3, etc. Okay, fine. Now, I have the first center as 0, radius is 1. Okay. So, first disk will be this is your D1, fine. D2 center is 5, radius is 1.5. So, 1.5 means here, that means this is 6.5 and this side it is 3.5, fine. So, now I will have the disk as, sorry, no, this is not 3.5, yes, this is 3.5. This is 4, na? 4 to 5, 1.5. So, 3.5 to 6.5. So, this is your D2. What about D3? D3 I have the center as 1, radius as 1.5. So, 1.5 means here it is 2.5 and this side it is minus 0.5. So, I have from here to here. So, I have the disk as like this. So, this is your D3. Understood? Now, your two eigenvalues will lie in D1 union D3, D1 union D3. So, maybe this is from -1 to 2.5. So, -1 to 2.5. This is one interval where your eigenvalue should lie, D1 union D3. The third one will be from 3.5 to 6.5. Okay? So, in this way very easily you can have an idea about inclusion of the eigenvalues for particular matrix. So, it was 3 by 3, like that I can extend 4 by 4, 5 by 5 just to have an idea of the eigenvalue region. Okay, fine. So, I think you know the few properties of the eigenvalues, such as if you have symmetric matrix, skew symmetric matrix or orthogonal matrix, what are the type of eigenvalues that you expect. Suppose the application problem that I had taken, if you see that it is a symmetric matrix, it is a symmetric matrix. So, what should be the type of eigenvalues? Means the eigenvalues will be real, imaginary or combination of these. So, we have different theorems that just I am writing. For symmetric matrix is with respect to real eigenvalues. If I complex eigenvalues, so I have what? Corresponding to symmetric, Hermitian. That means, for symmetric or Hermitian matrix, eigenvalues are always real. So, that whatever we had done for the application problem with respect to that, it was symmetric matrix. So, eigenvalues should be real. Okay. Second, for skew symmetric or with respect to complex matrix, it is skew Hermitian. I have the eigenvalues as, for skew symmetric, pure imaginary or 0. Third type is for orthogonal matrix. and in complex it is unitary. Here the eigenvalues will be what? Here if you find the eigenvalues, then the absolute values of those eigenvalues will be unity. Absolute values of eigenvalues is 1. So, these are with respect to some particular matrix, these are the type of eigenvalues that you get. So, seeing the type of the matrix, so you can have an idea that whether those will be real eigenvalues or pure imaginary or like this. Fine. Next, some other properties you have, you know what is trace of a matrix? A, sum of the AII. So, this whether I can have with respect to eigenvalues, trace, sum of all the eigenvalues. Okay. Another property I have, determinant of A, product of all the eigenvalues, that means lambda 1 into lambda 2 into lambda n depending upon the order of the eigenvalues. These are few properties, there are other properties, okay. You can see those. Now, so you have seen that eigenvalues depends upon the order of the matrix. Okay. So, if you have 50 by 50 matrix, fine, then how will you find those all eigenvalues, or whether we need to find all those eigenvalues? Whether we need to find all those eigenvalues for the practical purpose. One more term here you should know, that is a spectrum. What is this spectrum? The spectrum is what? With respect to other field, what is a spectrum? It is a range. Suppose with respect to optics, there you have seen the spectrum. Similarly, here a spectrum is what? A spectrum is the set of all eigenvalues. Okay? A spectral radius, similarly we have largest absolute eigenvalue, like that. Okay? So now spectrum means set of all eigenvalues. So, if I have 50 by 50 matrix, the spectrum is all those 50 eigenvalues. So, whether I need all those 50 eigenvalues to find practically. Suppose I take the same practical application that I was taking, I had taken that spring mass system or generalized, very generalized form of a building, very generalized form. Okay? So, whether, because if I have 50-story building, so whether I need to have all the 50 eigenvalues there, and what was those eigenvalues, what it was representing? Frequency are those eigenvalues. Now, whether I need all the frequencies to design a multi-story building or high-rise building. So, again design means what? Design means what? Design of building, design of car, design of anything, design of aeroplane. Design means so that it should not fail, subject to operation or subject to some force or what. Okay? So, that is the design, it should be safe. Okay? Safe means when I am giving some force to the building, whether ground or from the wind or whatever, okay, from earthquake or wind, it should not fail. That means when I have some forced frequency or some force, if it is force, some frequency will be there with that force. So, that means that force frequency I have to see that with respect to the natural frequency of the system. Those lambdas whatever we are finding, those are natural frequency, and those two should not match, natural frequency and force frequency. What will happen then? Resonance will occur. If resonance will occur, then it will fail. So, that means what I need? I need the natural frequencies, because I cannot expect what force frequency will come, because it depends upon the power of the wind or power of the earthquake. But for certain range I can have this through this, then I can have the safeness. So, that means main aim is to find this spectrum. So, suppose I have this lambda 1 to lambda n the eigenvalues, okay. I know this lambda 1 and I know this lambda. Suppose I, after finding, I this arrange this in increasing order or decreasing order, any order. So, this is the largest one maybe, and this is the smallest one. Now, if I know the largest and smallest, whether I can safely design, largest frequency and smallest frequency, because those should not cross, na. Lower bound and upper bound I need mainly for practical purpose. For other purpose, yeah, practical also others are needed. In general I am telling, that means you have now understood that I need to have only largest eigenvalue and smallest eigenvalue, all eigenvalues are inside that bound. If I know these two, practically it is done. Okay? So, that is why in general I do not need all the eigenvalues, although we have different methods to find all the eigenvalues, sometimes it is needed, but that is why in your course we will have only the method to find largest eigenvalue, and I will also give an idea to find the smallest eigenvalue. Those are very simple methods. This is done by a method that is known as power method, and this is just its inverse is called inverse power method. So, these two methods, this we will do, and I will give an idea for this only, inverse power method. So, this is little bit lengthy, but the idea is same, whatever power method algorithm or steps are there. So, in the next class we will do the power method to find the largest eigenvalue. So, that is why I told that we need practically only in general the lowest and highest eigenvalues, but in certain applications those are needed, other eigenvalues also. So, we have different methods to find those, we have different softwares also, you give the matrix, all eigenvalues you can find, okay, by giving one command. But here we will see first the how, using this method I can find the largest eigenvalue whatever order of your matrix is, and this is iterative method. This method is iterative method. So, here you are solving that characteristic equation, full we are solving lambda 1, lambda 2, lambda 3 depending upon your 3 by 3 matrix cubic. Okay. So, here whether it is 50 by 50, 25 by 25 matrix, I can very easily iterate that matrix with some criteria. You will have convergent, because it is iterative method, again you have to see whether it is convergence etc. is there. With some convergent series you will get from this method for the largest eigenvalue. So, in the next class we will do that power method. Okay. Thank you very much.